Okay, so this is exam number 3 from fall of 2019, and I loaded a blank copy into the past exams module. Okay, so I'm going to be putting the videos for these exams. Like if it's test 3 fall 2019, the videos will fall under that. And then I think I just uploaded like another exam maybe from 2018 or sometime, and they are underneath the copy of the exam itself. So again, when we get started, just again, a brief review. When I see normal, I have to go back to statics and think. I have normal, I have shear, I have a bending moment, and I could have internal torque. And with each of these forces, it's a force over an area. I'm going to end up with a stress. And so when I look at this stuff right here, this is my normal. That's what P is. I am literally stretching, okay? Stretching an object with a normal force. Normal just means perpendicular. Okay, it's perpendicular to the cross section, and it's a force over area, stress. When I put in then the material properties, I'm going to get strain, deformation. Strain is change in length. It is a change in length per unit length, so it's like a unit value, unitless. Okay. This is my equation for delta. If I were to rewrite this, if stress equals P over A and strain is delta over L, then I can rewrite this delta equals PL over AE. But again, this is only true in the elastic region. When I look over here, I have to recognize, again, this is torque. We are twisting. T. Torque. We have shear stress. If I were to put a little rectangle on the outside of this shaft as I were to twist it, okay, we can look at our, we can look like, think about it, just think about it. If I have torque here, like I'm wringing out a wash rag, as I'm wringing out that washcloth, we're twisting about our own centroid. So right here in the middle, there's no stress. It's not, that's what we're twisting about. There's no, if you think about a force times distance in statics, the distance to the centroid is 0. So there is no stress here. There's no, there's nothing happening. But as we move down this radial line, so rho is called a radial line, and rho, when it equals the radius, we call it C. Okay? C. C just means radius. Radius outer, radius inner. Rho is some length along that. We could say that max is TC over J. You may see that written. And that just means we are out here. Okay? So if you think about these fibers out here, as this is rotating, the fibers on the outside are having to twist ever so much more to make this system stay together, because we don't want the fibers breaking apart. We'd have failure. But they're having to really, like, kind of, and it's not really a stretch as much as it's a skew. If you think about a rectangle, when we go and look at this rectangle, it is really starting to skew over. Okay? Shear strain. We have that force, that shear force over the area, shear strain. Okay? So, as we look at this, we have force geometry, just like we had force geometry. And then we have, this is a function of our geometry. And then we have that same relationship. Shear stress, shear strain, G. Shear modulus of rigidity. And it's relating shear stress and shear strain. We have twist then, same kind of thing going on over here. And when we look at this, again, it's only in the elastic region. Okay, this is thin-walled. These are unique shapes, and here are material properties. And if we are looking at normal, which is axial, we have E, yield, alpha. If we are looking at shear, we have torque, we have G, shear modulus, and shear stress. So as we go through each problem, we need to identify, okay, I am seeing determine the angle of twist. This is telling me that it's going to be shear stress, angle of twist. I'm going to need a G. That's my shear modulus of rigidity. I might need a J. That's based on my geometry. of end A with respect to D. Okay? Determine the maximum shear stress. Here's another clue. It's telling us shear stress. Shear stress equals T. So I've already got the variables I know I've got to work with. TC over J. That's max. Okay? And J is going to equal, well, it depends on what shape I'm looking at. But for a circle, it's just T rho over J. Okay? This is for a circle. So we are going to have J is pi over 2 r to the 4th. So we can see that circular section, these others are going to have their own. So we have a thin-walled section. So this one's thin-walled. We have a square. And we have a circle. And we are looking, oh, we also note that it's torsion. It's the double arrows. I'm putting my thumb in that direction and twisting. So I know that this is my circle. Here's my circle. Here's my thin walled, and here's my square. So I'm just going to go ahead and get started. And what I'm going to do is I'm going to leave some room so we can find the internal resisting torque. But I'm going to talk about thin walled. So if I need angle of twist and shear stress, okay, angle of twist, the angle of twist of A with respect to D is going to be the twist from A to B plus the twist from B to C plus the twist from C to D. And I don't know yet. I don't know if any of these are backwards or forwards, okay? But I just know right now we've got this. I'll have to determine if there's a negative later, okay? So I know that that's going to be the answer to this question. And then the maximum shear stress, it's going to be dependent on their cross section. And the internal resisting torque. Okay, so if I have a thin-walled, cross section, my shear stress is T 2T A average, and my phi is TL over 4, that area mean, squared G. And we don't need the fancy, we're not integrating, it's a square, okay? So it's just going to be that length of our perimeter, so we can call that S, and thickness, okay? So as I'm looking at this, these are outside dimensions, so I'm going to draw a big kind of a picture here, and if I have to use 2 sheets of paper, I have to use 2 sheets of paper, okay? And I know that the outside dimensions are 7 inches and 5 inches, and I know that the thickness is 1/4 inch. So what I need is that center line, okay? I need the center line of this cross section. That's what I use for area mean. So I have to figure out where is that center line? What are the base and height? See how messy this is? I'm so sorry. Okay, I know it's got to be smaller than 7, but if I take 7 minus 1/4 and minus 1/4, so my inside is 6.5. I know it's got to be smaller than 7, but bigger than 6.5. Just like I know it's got to be smaller than 5, 5 minus 1/4 and 1/4, and smaller than 4.5, because it's that thin. So I could say it's 7, okay? I could say it's 7 minus that thickness divided by 2, minus that thickness divided by 2. And so I've got the thickness divided by 2 to come in, thickness divided by 2 to come in. Do you guys see that? Which leaves us then that inside dimension. And I could do the same thing here. 5 minus 1/4 divided by 2 minus 1/4 divided by 2. And so I've worked my way in 1/4 divided by 2, in 1/4 divided by 2, and I've got this nice inside piece. So if I do that, well, 1/4 divided by 2 and 1/4 divided by 2 is simply the thickness. So I have 6.75 inches and I have 4.75 inches. So when I'm looking at that area mean, that average area is 6.75 times 4.75. Okay. I also know that it is titanium. And if I'm dealing with shear, I am going to have a G of 6,400 KSI. And I don't have to check it against yielding because it didn't give me that yield allowable stress. So that's kind of what's going on here. Now I have a square. Okay, do you guys see the square? So if I'm looking at a square, then I can note that the maximum is 4.81 t divided by a cubed, and a is that outside edge. And I know that phi is 7.10 TL divided by a to the fourth g. And again, that's the outside edge. So a is 10. Okay. G, we are using steel. Steel. So I need to come back and get G, 11,000 KSI, and I need to get that yield stress of 21 KSI because I've got to check against yielding on everything I do. Okay. Now I have a circle, and I know that the max is TC over J, where J is pi over 2 C to the fourth. I know that phi is TL over JG, assuming I'm in the elastic region. Again, I have J. And my G is aluminum, so I'm going to come back here. G equals 3,700 KSI, and my shear stress is 25 KSI. So I can check that against yielding as well. Okay, so I now have the equations that I need. My phi is going to be this, or minus, whichever way it's going. My shear stress, I can find the maximum by finding the maximum of each of these and then picking the maximum. And so now all I need is this internal torque. Okay, you have to use statics. Okay, I'm coming across, this is all the same thing. So I'm going to draw a picture down here, and I've cut my section, and I have 2 kip feet going to the left, and inside I could have normal, I could have shear, I could have moment, I could have torque. And I'm going to sum torques in this direction, so I'm going to call that positive. So I have the torque from A to B. Okay, right hand rule, positive, 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 positive. Oh, that one's going backwards. Minus 12 kip feet equals 0. So TAB equals 12 kip feet. It is positive, so we're going to have a positive rotation. Okay, these are both positive. For the second segment, okay, I have 2 kip feet. How did I go from 2 kip feet to 12? Okay, I don't know how I do these things, so just go back and make that 2. Okay, 2 kip feet, and I have 93 kip feet, and then I have this section that I'm going to cut. And just like in statics, I could have normal, I could have shear, I could have bending moment, I could have torque. Okay, so I have torque from B to C. And I know that the sum of my torques have to equal 0. Okay, sum of all of my torques have to equal 0. So I'm going to start here. I've called torque BC positive. I'm using right hand rule. Okay, so I'm coming across, minus 93 minus 2 equals 0. So torque BC has to equal a positive 95 kip feet. Okay, so I know this is going to be positive, 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 positive. Let's look at our third section now. If I draw that third section, I'm kind of running out of room. I'm cutting. What do I find in statics? I have normal, I have shear, I have moment, I have torque. Okay, and this torque is from C to D. And I have 2, I have 93, and I have 283. So when I sum those torques, that way is positive. I have the torque CB minus 2 minus 95 plus 283 equals 0. So this time torque CB is negative, so it's twisting the opposite way. So I have 283 negative, okay, 45 plus 2 plus, and I get 236 kip feet. So now I have my torques. I know that this is negative and this is negative. I'm going to have a negative shear stress and a negative angle of twist. Okay. Sorry, the dog's going crazy today. I need everything to be in inches because I'm used to working with KSI and I don't want to work with feet. So I'm going to go ahead and put these lengths. So I have 8 times 12 and I have 96 inches. I have 60 inches and I have 48 inches. So I have my lengths. Okay. And I have this kind of organized, messily, but organized so it's easy for me now to go back and find my numbers. So let's, you guys work on this while I work on this. And so I'm going to find then the maximum shear stress for my thin wall. So I have T over 2T average, mean, whatever you want to call it. And the torque that I got was a positive 2 kip feet. We got to get out of that, so I have 12 inches per foot, divided by 2 times my thickness of 1/4 inch times 6.75 times 4.75. Everything is in inches, okay? Everything is in inches, and we're working in kip feet. We're making it all in inches, kip inches, so that we are in consistent units. So I have 24. 2 divided by 0.25 divided by 6.75 divided by and 4.75 divided by, and I get 1.5 KSI. So that's the torque, the maximum stress I get from the thin-walled structure. Okay, and I can go back and check. Okay, it doesn't give me a yield stress, so I don't need to worry about it. So this is from A to B. Torque B to C equals 4.81 T divided by A cubed. So I have 4.81, 12 inches per foot. That's for my torque. And I had an internal torque of 95 kip feet. That is not the units of torque. Hold on. Kip feet. So I'm getting rid of the feet, keeping inches, and my A is 10 inches cubed. Everything's in inches, everything's in kips. We're perfect. So I have 4.81, 12 times, 95 times, 10 divided by 10 divided by 10 divided by, and I get an internal resisting stress of 5.48 KSI. So that one's already bigger. This is already more big than that. So this one's already our biggest, okay? And now we need to find torque of CD. Oh, we need to check, is this less than yielding? Yielding was 21. So yes, this is less than yield stress of 21 KSI. Check. We can use those equations, okay? CD, T rho over J. That internal torque was negative, okay? Negative 236 kip feet, so 12 inches per foot, times rho. Well, the radius is 4 inches. When I go back and look, I was given a diameter, radius of 4. So I have 4 inches, divided by pi over 2, 4 to the 4th. When I work this out, I get 236, change signs, 12 times 4 times pi, remember 2 divided by, 4 divided by, 4 divided by, 4 divided by, 4 divided by. And I get negative 28.17 KSI. I go back to check yielding, and we have, it looks like we have yielded. Okay, it looks like we have yielded. And I think I screwed up my math somewhere, because I don't think we should have yielding on this problem. So let's see where I messed it up. I should have 236 times 12. It's 2832. Did I screw up my math down here? See, this is a good thing I checked yielding, because I can go back and make sure I didn't totally screw up. So I should have 283 minus 95 minus 2, 186. Or you can put 236. I don't know where that came from. 186. I am so sorry, my friends. 186. But see, that's why you check. Because then you're like, well, I don't have a stress strain curve, so I can't actually go back and find how much rotation we have. So I can't have possibly yielded. It just can't have possibly yielded. So I get negative 186. Not weird numbers like I got. 186, 12 times, 4 times, pi as a number. Whoops. Pi as a number, 2 divided by 4, 2, 3, 4. Negative 22. That is much better. Negative 22.2 KSI, which is less than my yield stress of 25. Check. Awesome. Okay. So where is my maximum stress? Okay. This would be the maximum stress. I'm actually, this time I'm wanting the largest number because I'm wanting to know what is the maximum stress in my system. This is by far the maximum stress. Okay. Now with rotation, I know it's going to be the rotation of A to B plus the rotation of B to C plus the rotation of C to D. Okay. So I just have to go back and use my formulas. Well, I have TL over 4AM squared G times S over T plus 7.10 TL divided by A to the 4th G minus, or we could say plus a negative, it doesn't matter, TL over JG. Okay, so now again, it's just plugging stuff in. My torque. Okay, if I look at my torque, it is 2 kip feet times 12 inches per foot times my length, 96 inches, divided by 4 times 4.75, 6.75 G, 6,400 KSI. So we're still in inches and kips, times, okay, times S. S is just that perimeter. 6.75 plus 4.75 plus 6.75 plus 4.75. It's that internal perimeter divided by a quarter. That's my thickness. Okay, plus 7.1 times 95 times 12. Got to get it in unit of inches. Times length 60 divided by A. Well, that's 10 to the 4th. And G, I already found 11,000. KSI, and I know I can use these equations because we haven't yielded. We are in the elastic. Plus, okay, I this time have a negative 186 times 12. My length is 48. Okay, my J is pi over 2, 4 squared, and my G is 3,700 KSI. If I were on a test, I would stop here, because you've already told me everything I need to know. You've shown me every single value I need. I don't need to know if you can use a calculator, okay? Because God knows I can't. So I'm not so concerned with that. I'm concerned with, do you know what the rotation is? Can you figure out negative values, positive values, actually the internal, what all these variables are, and you've more than defined them. Okay, so I would say move to the next problem, but we're going to go ahead and do this. So we have 12 times, 96 times. 4 divided by 4.75 divided by 6.75 divided by 6,400 divided by. And I get this very, very tiny number. Okay, and we haven't even finished. 6.75 enter, 4.75 enter, plus, divided by the thickness, and times, and it's a little bit easier number to read. Remember, these are in radians, okay? These are in radians. Then I have 7.1, 95 times, 12 times, 60 times, 10 divided by 10 divided by 10 divided by 10 divided by 11,000 divided by, and I have this tiny number. And I am a little bit concerned because this one is so much tinier than that, so I could have made a math error. But if you also look at those G, the G, that value that's on the bottom, there's a pretty, I think it's like a double difference if I'm looking at the right materials. The torque is bigger, but we also have these different geometries. So we'll see. And then those are both positive. I have this negative 186. Okay, I need to multiply it by 12 to get correct units. 48 times pi as a number to divide it by 4 times 4 times. This should be to the fourth. 4 times 4 times. Okay, divided by. And then I have 3,700 divided by. So I have that number, which is negative. And when I add them, I'm sorry. When I add them up, I get 0.19. 0.19 radians. This is in radians, okay? If I wanted to know the degrees, I know that I have, remember a circle? Okay, if I have 180 degrees, that's the same as pi. Or remember that 2 pi is 360 degrees, but I remember the 180. So if this is radians, that's like my pi. Pi goes on the bottom, 180 on top, and then I'll get units of degrees. I'm telling you guys, don't memorize the formulas, just look at your units. And I get a rotation of 10.9 degrees, which sounds pretty significant, but it doesn't look like anything yielded. And again, we're assuming that I can do all of my math correct. So this is how you would set up a problem, even if it was all the same roundness possibly. Sorry, I'm trying to do this again. Even if it was all the same roundness, you're going to set this problem up the same way. You have to find your internal torques. You have to figure out what your materials are, all of that kind of stuff. So this applies to any type of a cake torque problem. It's free to rotate, okay? And we have to find internal torques all the way down.